In chapter 4, we're going to go into an area of chemistry that is really the most important with regards to anyone who's interested in biology or medicine, and that is organic chemistry. Organic chemistry is just the chemistry of carbon, but all of the important functional molecules in your body are made of carbon. And so understanding the chemistry of carbon will help you understand biochemistry, which helps you understand medical things. So this is really key to understanding the body and how it works. Carbon is extremely flexible because it can make chains to itself, and it bonds with just about any other element in the table. Unlike most elements have a limited chemistry, carbon has this huge amount of chemistry. So we're going to look at carbon, and we're going to see that it can make single, double, and triple bonds. We've seen that when just doing Lewis dot structures, and it bonds to oxygen and nitrogen, and that accounts for a huge amount of its chemistry. So let's go ahead and dive into this. Remember how carbon does bonding. This is going to be important for you to properly do organic chemistry, and that is 4 bonds on carbon. Oxygen, 2 bonds and 2 non-bonding pairs. And something that you're going to hear me say, and you'll read in the book, is that atoms other than carbon and hydrogen are called heteroatoms. So oxygen, nitrogen, halogens, those are all what we call heteroatoms. Carbon and hydrogen are the basis of organic chemistry, and the other things are part of it, but we call them heteroatoms because they're different from the basic of organic chemistry. Every hydrogen has just 1 bond, and when you take a hydrogen off of an oxygen or carbon, it has a positive charge. And then the halogens have 1 bond and 3 non-bonding pairs. And last of all, nitrogen with its 3 bonds and 1 non-bonding pair. Sometimes you will see nitrogen with 4 bonds, but when it does, when you do, it has a positive charge. All right, we're going to look at several different ways of writing compounds. One is the molecular formula that you're already familiar with, and that just tells you how many atoms are in a molecule. But there's something else called an empirical formula, and that is just the simplest ratio of the elements to each other. There's the structural formula, which actually shows how the bonding occurs. A condensed formula that is you get an understanding of the structural formula because you understand bonding. And then the line drawing, which eliminates all atoms except for heteroatoms and hydrogens attached to heteroatoms, but you see the structure of the molecule. And then 3-dimensional drawing, which is what we call a wedge and dash drawing. And let's go through these so you can see them. Here is the molecular formula of an organic molecule called butane, C4H10. And all it's showing you is that there's 4 carbons and 10 hydrogens in the molecule. An empirical formula simplifies that ratio. 4 to 10 can be simplified down to 2 to 5, and so the ratio of carbon to hydrogen in butane is 2 to 5. The structural formula shows how the atoms are bound to each other. So if we look at butane, we can see there are 4 carbons in a row and then hydrogens all around. The condensed formula gives you that same information, but it's not showing the bonds. You just have to know that the hydrogens are attached to the carbon, and the carbons, because they're lined up like that, are all attached to each other. Next, we have the line drawing, and we draw molecules like this, and we're not showing any atoms in this drawing at least, but this represents a carbon bound to a hydrogen, bound to a carbon bound to a carbon, bound to a carbon, bound to a carbon, and we know that there are hydrogens enough around all the carbons to make it have 4 bonds. And then the wedge and dash drawing is actually giving you a three-dimensional picture. In this picture, we have carbon, 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 all in the plane of the screen. This hydrogen is coming out at you, and this hydrogen is going back behind the screen. This carbon is coming out at you, that hydrogen is going back behind the screen. And we use this when we want to emphasize the three-dimensional arrangement of a tetrahedral atom. You see, here and here, carbons are both tetrahedral, so we're actually showing how it arranges in space. These carbons are also tetrahedral, but we just didn't bother to show their three-dimensional drawing. Now, the condensed formulas are, you need to be able to understand how they work. And so I've taken butane and I'm showing you how the condensed formula works. We know that carbon has to have 4 bonds and hydrogen can only have 1. So if I look at CH3 down here, I know that those 3 hydrogens must be attached to the carbon and that this carbon must be attached to that carbon. So in all of this drawing, we actually are looking at how the atoms are attached to each other with our understanding of how they must be bonded, instead of seeing every single bond. So every organic formula tells you the connectivity, and sometimes we have double bonds and heteroatoms in there, but we can still decipher how they're connected based on these rules that the hydrogens are attached to the carbon that they follow or the atom that they follow, and that they are connected in a certain way. So now what I want you to do is try to do this yourself. Draw out, this is a molecule called ethane, and I want you to draw out all the bonds in it in what we call the structural formula. And when you get through with that, go ahead and try to do this one also. Well, the structural formula for ethane is, because the 2 carbons are in a line, they're attached to each other, and then these hydrogens must be surrounding the carbons. For this molecule, we have carbon attached to carbon, attached to carbon, attached to oxygen. So we put them in a row like that. Then there's a double bond between these 2 carbons, right there, and a double bond between the oxygen and the carbon, so right there. And then the hydrogens are attached to the atoms that they follow. Condensed formulas can also use parentheses. Here, when we put, this is what we call a methylene group, and we'll understand that later. When we take a methylene group, CH2, and put it in parentheses, it means they're all lined up in a row. So here there's, this is actually butane because there's 1, 2, 3, 4 all in a row. If I have it on the end of a molecule, then the parentheses, and you see this is what we call a methyl group. So this CH3 inside the parentheses, there's 2 of them attached to this carbon. And so there you can see that. One thing that we find in organic chemistry is something that we call structural isomers. There's this huge variety of molecules that we can have, and we find that some of them are related by their molecular formula. So if you look down at this example down here, you see there are 3 carbons and 3 hydrogens. This molecule is bound together differently than this molecule. Because they have the same formula, but they're connected to the atoms are connected to each other in a different way, we call them structural isomers. So what we will find later on is anytime 2 molecules have the same formula, but they have different names, they end up being structural isomers. Last, what we're going to do in this online lecture is introduce you to the organic shorthand, which is the line drawings. Condensed formulas, except for just the smallest molecule, take forever to write, and they're actually kind of hard to understand because there's so many hydrogens in there that it takes away the emphasis of the carbon backbone and the heteroatoms, which are what are most important. There is something we call line drawing or organic shorthand or skeletal structures. This gives us the carbon backbone and shows the heteroatoms and assumes that you understand how molecules are put together. And what this does is it emphasizes the structure of the compound without eliminating any information. So let's look how we do this. Here we have 3 carbons in a row. This is called propane. How is it that we draw this in the skeletal structure? Well, every line segment is 2 carbons that are attached to each other. So if I look over here, there's a carbon here and a carbon here, 2 carbons attached to each other. But there's the same carbon here and then another one here. So I can see right at a glance that it's 1, 2, 3 carbons in this molecule. What about the hydrogens, you might be thinking? Well, we know how many hydrogens there are because in every compound, carbon has to have 4 bonds. And where the hydrogens aren't shown in the skeletal structure, we know how many they are because the rest of the bonds must be to hydrogen. So right here, let's go to this atom right here. You can see it has only 1 visible bond. That means there must be 3 hydrogens attached. This carbon right here has 2 visible bonds, so that must be 2 hydrogens attached. And we can figure that out in all of them. If we look at this structure, there are 4 carbons in a row, 1, 2, 3, 4. And then on the second carbon, there's another carbon right down here. So we can see this structure and we know how many hydrogens are in each atom. 3 because 1 bond, only 1 because 3 bonds shown, 2 because 2 bonds are shown, and 3 because 1 bond is shown. And then down here, 3 because 1 bond is shown. So this takes a little practice, but with time you're going to see it very quickly. We always show double and triple bonds in our shorthand. They're very important as they're different from the rest of the molecule. And we always show heteroatoms. Now with the heteroatoms, many students will get confused because they will look at the bond of a carbon, from a carbon to a heteroatom, and they will think there is a carbon at that end of the bond to the heteroatom, but there is not. So be very careful in looking at these. So if I look at this molecule as it's written, there are 1, 2, 3, 4, 5 only carbons. There is no carbon here. Likewise, here you have 1, 2, 3, 4 carbons, and there's a double bond between the 2 inside carbons. Something that we use a lot is this thing that we call an R group. You can think that it stands for the rest of the molecule, and R means just any carbon chain. Another abbreviation that we use is X. X stands for any halogen. So here, this X can represent fluorine, chlorine, bromine, and iodine. When we put an R group on, realize it can mean 1 carbon or it can mean 42. It doesn't matter that we're not focusing on that part of the molecule. What we're focusing on is the part that is drawn